Our efforts eventually focused on triangular steel prisms, which could be tripolar or bipolar. Tripolar reactions could be achieved with 1, 2, or 3 magnet sources, while bipolar requires linkage between 2 magnets. Two boundary reactions seem to have the most utility in both glass and steel prisms. Net forces in a tripolar reaction are 0, while bipolar reactions the net force is non-zero with much more potential. So our experiments took the form this scenario is where we wasted most of our time and money. A rectangular steel block would gravitate to the center of the magnets, while a triangular steel prism would gravitate towards one end. No motion will occur with so-called homopolar magnets. A very low power perpetual motion machine might alternately stagger top and bottom magnet sets with the right spacing and achieve spin. More important, we realized all reactions with these components could be predicted using refraction principles, Snell's law, and the force equations from Magnetics 101. Our discovery is just that simple. Maybe the time and money wasn't wasted after all. So we came to a whole bunch of conjecture. The refraction of light and magnetic flux can be resolved with Newtonian forces. For light, the forces are frequency and wavelength dependent, thereby producing rainbows within a narrow range of angular conditions. For magnetic flux, the angles and the range of conditions are similar, but the forces are comparatively enormous. Induction and magnetic attraction forces are perpendicular vectors. Refraction alters the ratio of the two vectors. The ratio can only be changed by altering the flux gradient, which requires a potent force. The potent force can be theoretically isolated, but must be produced in tandem reactions. Faraday's forces are typically defined in an incomplete circuit, with current passing through short lengths of wire. Typical motors complete the circuit, with tandem reactions producing torque proportional to the distance between the tandem reactions. Likewise, lenses, magnifying glasses, and our discovery are dependent on tandem reactions at two boundaries.